Hello everyone, I am Mark Edward Gonzales, the current president of the Peer Tutor Society, and in this student tutorial video, I will be talking about integration by parts. So integration by parts is a technique in calculus that allows us to take the integrals of more complex expressions. It's usually considered one of the final bosses in ST Math, that is integral calculus for software technology students, a course usually taken by our sophomore students during their second term. So without much further ado, let us begin. But first, where does the idea of integration by parts come from? So to understand this, we have to backtrack a little bit and try to recall the product rule related to derivatives, which we have learned back in CS Math 1. So suppose we have two functions f and g, take their product, then we take the derivative of their product. This would be the derivative of f times g plus f times the derivative of g. Okay, now since we are after an integral, it makes sense to integrate both sides. Let's integrate both sides. Let's make the integral sign more pronounced so that we don't confuse ourselves. Okay, fully split this into two separate integrals. And just copy the left-hand side. Notice that we have the integral sign here, then we have the derivative over here. This would imply that they would cancel each other out. So we're just left with the product of f and g. And we copy the right-hand side of the equation this time. Plus, take off this one. Now we're stuck. It looks nice. There seems to be alternating patterns, but we're not exactly sure what this thing entails. And it's rather unwieldy. So maybe it would help for us to do some substitutions, which we have learned during the first part of the ST Math course. Let's suppose that u is equal to fx and v is equal to g of x. This would mean that du is equal to the derivative and dv is also equal to the derivative. Okay, and then we do some matching. Notice that over here, f, oh, that's u. Do we see any other instances of f? Here, we have this one over here. Maybe it would help for us to transfer this. So this is u, and this is u. Okay. Now, for this one, v equal to g of x. This is g. This is g. So we see the presence of v here and the presence of v here as well. Let's go to the next ones. Here, du is the derivative of f of x, which happens to be this one. And now we see du. And finally, dv is the derivative of g of x. And we see it over here. This one is dv. And then we just copy the remaining stuff on the board. Okay, so rewriting things just to be a little bit clearer, we have uv is equal to the integral of v du plus the integral of u dv. Sounds like a tongue twister. So we just transfer this here, transpose, and we will get uv minus the integral of v du is equal to the integral of u dv. And we just switch both sides and we get the familiar form. The integral of u dv is equal to uv minus the integral of v du. This is the formula for integration by parts. Again, the formula for integration by parts is given by the integral of u dv is equal to uv minus the integral of v du. It sounds like a tongue twister, but let's admit it, it's rather cute and perhaps a little memorable. Again, the integral of u dv is equal to uv minus the integral of v du. In summary, integration by parts is actually a consequence of the product rule of derivatives. So I hope that this helps demystify the concept a little bit. In any case, let us now start to get our hands dirty and try out some examples. The examples that we will be discussing in this tutorial video, in the student tutorial video, are taken from the website of the mathematics department of UC Davis. All credits go to them. Let's clear the screen and transfer this formula to the top of the board. So we have a reference for our first few examples. Okay, let's start with the first example. We want to take the integral of x multiplied by e raised to x dx. The natural question to ask is which one is u and which one is v? So which one is u? Well, we have two choices, at least two choices. Perhaps this is u. Okay, that's one possible choice. Or maybe this one is u. Well, to be very honest with everyone, we don't actually know which one is u right at the beginning. We have to do a little bit of guess and check, a little bit of trial and error. Well, we can reduce the amount of trial and error through a bit of intuition and loads of practice and experience. But essentially, it's a guess and check. If it doesn't work in the first try, then we just backtrack and try again. And there's no harm, there's no shame in doing that. After all, such is the essence of calculus, such is the essence of mathematics. Great insights may take some time. They may take a little bit of trial and error in order for us to arrive at those insights. In any case, what if we let u be equal to e raised to x? So it's a what if. So let's just rewrite the things to be a little bit clearer. If we let u to be equal to e raised to x, then this would imply that dv is x dx. That is the implication. Okay. du is e raised to x dx. And v here would be equal to x squared over 2 because we are taking the integral of x and that's x squared over 2. What would happen if this is the case? Following the formula, that's uv. It's this one. Let's transfer this to the right side of the board so that we have more space. U is e raised to x. V is x squared over 2. V is x squared over 2. And du is e raised to x dx. Well, the minuend kind of simplifies nicely. But the subtrahend is a big problem. This is a big mess. We don't even know how to get the integral of x squared over 2 multiplied by e raised to x dx. So it's a big mess. This already signals to us that we have chosen the wrong u. So big X. Again, it's a guess and check. There's no shame in being wrong in the first try. Actually, it's normal to be wrong in the first try. It's less normal to actually know what u is in advance. Well, admittedly, there may be some patterns that will emerge as we solve more examples. And while patterns are helpful, especially in environments where we are under time pressure, such as exams, midterm exams, quizzes, or seat works, over-reliance on patterns does more harm than good. It, to an extent, kills a little bit of the drive, the curiosity, and the critical thinking. So patterns are good, but over-reliance on patterns does more harm than good. In any case, now that we know that u is not equal to e raised to x, the next natural choice would be to let u be equal to x. So let's try to see what happens if we do that. So we just clear the whiteboard. Okay. It's quite hard to erase this in any case. Let's suppose that u is equal to x. Now it follows that our dv will be the rest of the expression. The derivative of u will be equal to dx, and the integral of e raised to x is also e raised to x. Okay, let us now perform integration by parts. The integral of u dv is equal to ub minus the integral of v du. A very, very cute formula to say. U is x, v is e raised to x. V is e raised to x. You can also follow the color code that we have here. Du is equal to dx. Simplifying, we get x multiplied by e raised to x. The integral of e raised to x dx is equal to e raised to x minus e raised to x. Oops, plus c, the notorious constant of integration. And there we have the answer. The integral of x multiplied by e raised to x dx is equal to x multiplied by e raised to x minus e raised to x plus c. Okay, so we can pause the video if we would like to get some more insights or reflect some more on this problem. Moving on to the next example. So we're going to solve several examples in order to reinforce and build our understanding of the idea of integration by parts. For the second example, we have this. Which one is u? Which one is v? Again, we can obtain the correct values through trial and error. So let's not be afraid to do a little bit of guess and check. After all, it's part of life. So in this case, let's have u be equal to x. The rest of the expression will then become dv. So dv will be sine x dx. So let's use color coding so that things look a little bit nicer. So this will be dx, and here the integral of sine would be negative cosine. We have this. The integral of u dv is equal to uv minus the integral of v du. U is x, follow the color coding that we have here. V is negative cosine x. V is negative cosine x. And du is dx. This simplifies to negative x cosine x. Negative here. So we have positive sine x dx. The integral of cosine is sine. So we have negative x cosine x plus sine x plus our favorite constant of integration. And this is the final answer. You can pause the video to give it a try. And we proceed to the next example. So for the next example, let us consider the integral of x ln x dx. Which one is u? Which one is v? Again, I might sound like a broken record, but it is a matter of trial and error with a little bit of luck, or let's call it intuition, and loads of experience and practice. So, in this case, let's have u as x. Would that be the correct one? Well, it would be nice to pause the video and try it out yourself to see why setting u to be equal to x is actually a very bad idea. So it really is worth the try. In any case, the correct substitution would be to let u and equate it to ln x. This then implies that the rest of the expression is dv x dx. Again, it is a good idea, an extremely helpful practice to try and see why things don't work out and why some things work out. This is true in mathematics, in life, and perhaps in relationships as well. Anyway, without digressing too much, du would be equal to 1 over x dx. Here, take the derivative of x, that would be x squared over 2. Or rather, the integral of x, that would be x squared over 2. Integration by parts, u dv, the integral of u dv is equal to ub minus the integral of p du. U is ln x. We follow the color coding just to be clearer and a bit more visual. And v is x squared over 2. Integral sign, v is x squared over 2. And du is 1 over x dx. We then proceed to some algebraic simplification. This is x squared ln x over 2 minus cancel, that's x over 2 dx. Okay, we just move this upward to give us more space. So x squared ln x over 2, we factor out 1/2, leaving us with the integral of x dx, and the integral of x dx, as we have mentioned a while ago, is equal to x squared over 2. We can also use the power rule to verify this. Okay. Plus c, constant of integration. So x squared ln x over 2 minus x squared over 4 plus c will be our final answer for this one. Okay. For our next example, the box and the squiggly boys are left. Let's try to take the integral of this thing. Again, these examples are taken from the website of the mathematics department of UC Davis. Now for this one, which one is u, which one is v? We'll let this be equal to u. So the rest of the expression will be equal to dv rather. Take the derivative of u, we take the integral of dv. So since we have 3x here, we have to offset the 3x by multiplying the thing with 1/3, and the integral of cosine is sine. If this might be a little bit too quick for now, then we can use the usual u substitution to solve this. However, it also helps to be a little bit accustomed with playing around substitutions and chain rule. So if we take the derivative of this one, we'll see that the 1/3 will counteract the 3 from 3x. In any case, let us continue. So we just remove this dot over here and diffuse this a little bit more aesthetic, I guess. Okay. So integration by parts. Color coding. U is x. V is 1/3 sine of 3x. 1/3 sine of 3x. And du, the derivative, is equal to dx. We proceed. This is x over x sine 3x over 3. Now, this one, let us recall that the integral of sine is actually negative cosine. Well, in any case, let's factor out 1/3 first. Just so we just have sine 3x over 3. Let's move our solution. here. Once again, the integral of sine is negative cosine. Since we have 3x here, we have to offset this by multiplying the entire thing by 1/3. And the constant of integration. Negative here, that means things will be positive. Thus C. And this is our final answer. Okay, so now we have seen an example wherein x is multiplied by a trigonometric function. Let us now go to some more examples. So you might have noticed that patterns are beginning to emerge. But once again, a small caveat, over-reliance on patterns does more harm than good. But patterns are a good thing.